Hey y'all, today we're going to look at light, and specifically we're going to start connecting some of the variables associated with light energy. We're going to look at a single photon at first and then talk about how energy scales with the number of photons that we've got. So let's go ahead and get started. Keep in mind is that a photon of light can act as both matter and energy. And as such, we can treat it the same way we would treat anything that has both mass and energy. In AP chemistry, we're going to focus mostly on the energy side of this equation. So we're going to use variables and equations that have to do with energy, wavelength, and frequency. Let's go ahead and take a look at how we're going to use these calculations to find each of the variables of a photon. Let's start with wavelength. The wavelength of a photon is the distance between the two peaks of its wave. So as a photon is traveling through space, it has this property of a wave, which looks like, well, kind of like the wave of an ocean wave. And when you see the wave, there are peaks and there are troughs. And so if you measure from peak to peak and you take that distance, that's the wavelength. So wavelength is measured in a distance. Normally, we're going to see it measured in nanometers. However, sometimes you will see it in other units such as centimeters or meters. Wavelength is represented using the Greek letter lambda, okay, which looks a little bit like an upside down Y. All right. And so whenever you see that variable, that is wavelength. The next unit we're going to look at is frequency. The frequency of a wave is going to be the number of times that peak happens each second. So one way we say this would be oscillations per second. Or in the case of frequency, we're using just the unit hertz, H-E-R-T-Z, which is just seconds to the -1. The variable we use to represent frequency is the Greek symbol nu, and it looks a little bit like a V. So sometimes I'll actually call it V just to make it easier to speak it out. When calculating the energy or the wavelength or the frequency of a single photon, we're going to utilize mainly two different equations that are on your formula sheet. These two equations connect to each other, and we're going to talk about how they connect to each other in a moment. That's going to give us a third equation. But first, looking at the two equations that are on your formula sheet. The first equation is c, which is the speed of light, is equal to lambda, which is the wavelength, times nu, which is the frequency. So lambda times nu is equal to the constant, which is the speed of light. Now be careful. Speed of light on your formula sheet is given in meters per second, 3 times 10 to the 8th meters per second. Meanwhile, the wavelength is often given in nanometers or seeking nanometers. So be careful when you're doing this equation. You want to make sure your units are matching. But that's the first equation here. Now, if we're going to analyze this equation a little bit further, keep in mind the fact that because wavelength and frequency are both on the same side of the equal sign, they're inversely related, which means as the frequency goes up, wavelength comes down, and as frequency goes down, wavelength goes up. The next equation we're going to look at is for the energy of a single photon. And again, this is important. This would be the energy of one photon. And the energy of one photon is going to be equal to the frequency of light, nu, times h. And h, which is on your formula sheet, is Planck's constant. Planck's constant is equal to 6.626 times 10 to the negative 36 joule seconds, which is joules times seconds. Okay? So if we take that number, Planck's constant, multiply by our frequency, what we'll end up with is the energy in joules of a single, that's one photon. Now keep in mind, because energy and frequency are on opposite sides of the equal sign here, they are going to be directly related. So as the frequency of light goes up, so does the amount of energy of that photon. Let's get to that third equation I was talking about. Even though there's only two on the formula sheet, oftentimes you're going to have to manipulate each of these to be able to acquire the energy if you were, say, given the wavelength. There's a very easy way to do this using a little bit of algebra. That's going to be to take those two, recognize the fact that the frequency is the same in both. You're going to solve for frequency, and you're going to go ahead and plug it in. Because of that, we get the energy of a single photon is equal to Planck's constant times the speed of light divided by the wavelength. So this is our third equation. But again, this is not one that you're going to see on your formula sheet. This is one that you're going to have to manipulate two equations to get to. But it's another one to have in your back pocket and be aware that even given the wavelength, you can find the energy of a photon pretty easily. Let's get to our first example where we're going to apply this. Here I've got a laser, and this laser has a wavelength of 514 nanometers. Again, nanometers is a really important unit here. Remember, a nanometer is 1 times 10 to the negative 9th meters. So if we have 514 nanometers, it's 5.14 times 10 to the negative 7th meters. And you get there by dividing by 1 times 10 to the 9th. Okay, so you can see my first step here is to get my units right. I'm going to go from nanometers to meters. The reason I need to do this is because my speed of light that I'm going to use is in meters per second. So I need to match units. Then I'm going to use the equation c, which is the speed of light, in meters per second, is equal to the wavelength, which we just found to be 5.14 times 10 to the negative 7th meters, times the frequency, nu. In order to solve this, we're going to divide both sides by 5.14 times 10 to the negative 7th, and our frequency is going to equal 5.7 times 10 to the 14th hertz, or remember, inverse seconds. Now that's to find our frequency. We now need to use this information to find our energy. So I'm going to go to my second equation. And in the second equation, what I'm going to do is I'm going to plug in that frequency we just found, multiply by Planck's constant, and I get the energy of that one photon with a wavelength of 514 nanometers to equal 3.84 times 10 to the negative 19 joules. And remember, that's just for one photon. All right, we did one together. I want you to do one on your own. Here I've got an example problem, and I want you to try it. A single photon has energy equal to 6.9 times 10 to the negative 7th joules. I want you to find for me the wavelength of that photon. So if you need to take a second to pause the video, do it. When you're ready, come back and we'll talk about it. All right, so did you get the answer? Now, there's a shortcut here. If you wanted to memorize and use that third equation we talked about, E is equal to H times C over lambda, you could have used it here. But be careful, you need to make sure that your units match, okay? So when we do this, what we're going to do is we're going to solve for that wavelength. So we're going to multiply both sides by the lambda. We're going to divide both sides by E. If you plug that equation in, you get 6.626 times 10 to the negative 34th times 2.998 times 10 to the 8th divided by your energy of 6.9 times 10 to the negative 7th joules. Make sure you know the units you're working in. Speed of light is in meters per second, okay? So we are going to get an answer here that's in meters. When we solve it, we get in meters 2.86 times 10 to the negative 19th meters. If I needed to convert that, I could do so. I could convert that into nanometers by multiplying by 1 times 10 to the 9th. All right, but in this case, I'm just going to go ahead and leave it in meters. So that wraps up today's video. Let's do a quick recap. Today, we learned how to utilize the light equations on your formula sheet. We determined the relationships between wavelength, frequency, and the energy of a photon. One thing to keep in mind is all these equations are talking about a single photon. There are going to be times where you're looking for perhaps the energy of more than one photon. And if that was the case, you would just simply multiply by the number of photons you have. Okay? Very straightforward calculations, but it's really important to be able to do this properly so that you can move forward with the content. Today's video was written, directed, produced, and edited by Sarah Luna Sassin. I'd like to thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one. How was that?
Variable.
Son of a... Okay. The variable associated with frequency is the symbol nu, which kind of looks like... You couldn't hold that one in, could you? No. Bless you. This is why I kick people out. All right. And that's a wrap.